Hello, this is Desiree Duvenet, Professor of Medicine at the International Medical University. Today we're going to be talking about electrophysiological-reactivity. Back in 1989, we got this registered at the FDA with our biofeedback device, a device that we could measure the electrophysiology of different nosodes, hoursodes, sarcodes, etc. Being able to measure how a person reacts to a trivector field, a field that we would make with a Voltammetric device. This is very interesting and was a hallmark of science and law to be able to register in 1989, along with the VARHO, being able to measure the voltage, amperage, resistance, hydration, oxidation, and acid-alkaline imbalance. So thus we were able to start to really measure the body electric.
The basic idea is that there is a body electric. That is obvious because what we are is a collection of electrons. If we took all of the grains of sand on the entire planet Earth and times it by all the stars in the sky, we still have more electrons in the human body, and the electrons don't touch. We are basically a very large, vastly complicated electromagnetic field. The electrons are held together through electromagnetic static forces, quantic forces, photonic forces, and all these other basic principles of energy that make what we are. Now, the shark was first found to have a system in his nose to be able to detect electrical phenomena at a distance.
All sharks are attracted to the weak electromagnetic fields of their prey, but it's thought that the hammerhead's extra-wide head shape gives it an especially sensitive detector. To find out just how sensitive, Steve is using electric currents to create these fields and see what field strength they can detect. The circle of cable on the left has a current running through it, while the one on the right has none at all.
How minor is this current we're talking about? This current that you're putting in here?
Right.
How minor is it?
What I'm applying right now is 7.7 microamps, 5 nanovolts per centimeter, 5 billionths of a volt per centimeter.
It's an incredibly small figure.
The way to think about that would be to take a standard flashlight battery and stick one lead in the water in Boston, and the other lead in the water in Miami. And a shark swimming directly between those two leads would be able to detect that minute amount of current flowing between those two leads.
Just a little torch battery.
That's right, that's right.
And that's about 1,500 kilometers or so.
Right, what's that? Yeah. It's tiny.
That's amazing.
Yes, an amazing display of the electrosense.
Even though they look identical, the target on the left attracts all the shark's attention. So Steve knows they're not attracted by visual cues, just a tiny magnetic field.
We now find out that that same type of electrical analysis, that electrosense that we all have, as Spidey tells us, we all have an electrosense. That electrosense is in the human being been translated into the nasal pharynx and also all the different cells of the body. But the nasal pharynx has the most intense collection because this is where the shape receptors are. Now, for the shark living in salt water, there's a direct electroconductivity between the substances that have an electrical field and the shark's nose. However, in air, as we live in, the air is not electroconductive. So thereby we have taste sensors in the tongue and nose and shape receptors that allow those things to come in and touch. Now,
The tongue works as a small voltammetry device to be able to sense the trivector field. It's done through the taste buds to be able to taste sweet, sour, salty, bitter, and all these other different flavors. But now, little things that happen to us, little things we are exposed to in the natural world, will come into the tongue or the nose, and then we can sense that field. It's not absorbed in the tongue, but it is meant to measure the shape receptor, to see the shape. And once that shape gets in and gets reactive, This information will pass from the taste bud through the nervous system and be able to transmit into the brain so that the brain can determine what to do for digestion, what to do for hunting. The little neurons inside the nose are also very similar. They're shape receptors. Shape receptors fill all the cells of the body, but they're most prevalent in the nasal pharynx, in the nose and in the tongue, to allow us to measure shapes, to perceive our environment. Things that will come into this as we smell them, you see, because we're not in salt water like the shark, so these things are carried through the air and we have to touch them rather than have the salt water convey that. But as things go into the body and they're touched, this information will be communicated into the brain. Much of this will go to our unconscious and a little bit go to our conscious mind. The word area or conscious mind will be able to tell what it is receiving through smell and shape recognition, and then verbal recognition. The body unconscious, the body electric, will be able to experience all the different things that are happening throughout the entire. The shape receptors act as a type of voltammetry detector to measure the electrical shape and then stimulate certain neurons to go to the brain to help it to understand what is in the environment. Without the salt water in an air environment, we would need to be able to contact these things through the smell.
Shape receptors. Now, in the study of voltammetry, be able to study the electromagnetic signature of an item. We've taken that science and tried to build a basic little system, a voltammetry system, that would work like the tongue to be able to measure the shape. Then we would take these electric shapes that we have measured with the patented system known as the QQC, and with the QQC we're going to be able to take those substances, amplify them millions of times to be able to get a similar reactivity as that of the shark. In other words, the electromagnetic field of an item is measured, then that is stored in the hard drive of the computer, in the quantum coherency test kit, inside the SCIO system, and thereby it is then activated when we test these substances to a person to see how they react. It is very much through an electroconductivity process.
Here's a picture of our modern-day voltammetry device that we got from a Swiss company, and it allows us to take a three-dimensional picture of the electrical trivector energy flow of a substance. It's basically an electronic tongue, and it will draw us a voltammetric picture. The picture that will look something like this. Here's a sample. So as we are changing the voltage, we are going to be getting an amperage reading. As we change amperage, we get a voltage reading. And then combine this with a capacitance reading, we can get a three-dimensional reading and get a trivector energy shape. Send this into the patient, then we can measure the reaction. Over 30 years of research on the electric tongue and the abilities for us to be able to do the electro-physiological-reactivity in a host of different ways, blood analysis, hair analysis, correlations, etc., have shown that the system works at a level that can start to get us some ideas with our patient. From these ideas with the patient, we want to take it further and try to validate and verify our hypothesis. So we don't just take the EPR as absolute gospel, we try to then challenge it and find out more. So now we've studied about the electrophysiological reactivity.